And welcome to our course today. My name is Tom Irvine, and this is an introduction to shock and vibration, or we might say introduction to vibroacoustics. So here's Nikola Tesla, and he said if you want to find the secrets of the universe, think in terms of energy, frequency, and vibration. So that's what we're going to do today, although our focus, at least immediately, will be on launch vehicles or rocket vehicles. So on the left is an Ares 1X launch vehicle, unmanned. It was a NASA launch back in 2009. And at the front, you can see what's called a Prandtl Gelert singularity vapor cone of condensed water. And that's not really of immediate interest in terms of shock and vibration, but it's still pretty interesting what's going on there, and it could have some effect on vibration. And of course, we have the solid rocket first stage burning there, creating a lot of structure-borne vibration. There's also sound being produced in that exhaust plume, and some of that sound then will propagate back into the launch vehicle. Now, on the right, we have a flight accelerometer data from an accelerometer at some point on that launch vehicle. So the y-axis is acceleration in g, and the x-axis is time in seconds. There's a number of events that occur. So at the onset here, we have the launch acoustics, liftoff acoustics. And then there's a period of, during ascent, of subsonic, where the levels are relatively low. And then as the vehicle starts to approach the transonic velocity, then it goes transonic, and turbulent boundary layers forming, aerodynamic shock waves forming, and it encounters its maximum dynamic pressure, also known as the max Q condition there. And then for several dozen seconds, those turbulent boundary layer and other effects are persisting, and then the vibration envelope tends to taper off a bit anyways. So that launch vehicle has a number of components, electronic components, battery boxes, antennas, moving mechanical assemblies, and also thrust vector control actuators and so on. And those components need to be designed, analyzed, and tested to withstand the vibrations, such as shown in that top right acceleration time history there. So on our next slide, we have maximum predicted environments. So for each of our components, we need to come up with an MPE level. And in the launch vehicle world, those MPEs can be derived from a number of sources. So off to the left there, you see stage and fairing separation tests. So stage separation is typically a pyrotechnic device, linear shape charge, frangible joint, V-bands with bolt cutters, explosive bolts, explosive release nuts, and so on are used depending on the type of vehicle. And we do ground tests to actually set off those pyrotechnic devices and measure the source shock as well as the shock energy as it propagates through structural material and joints to wherever the components are mounted. Wind tunnel testing is done to look at what's going on with turbulent boundary layers and aerodynamic shock waves. Solid motor static fire tests. And in the case of liquid engines, they're called hot fire tests, although they're really all the same thing. The motor engine is bolted to a test frame, fixed to the ground, so it has zero net displacement. And then the motor is ignited or the engine is ignited, and then that gives a chance to measure vibration among other important parameters. Modal tests, we'll talk about that later. That's to experimentally measure the natural frequencies and corresponding damping ratios and sometimes even the mode shapes. Shaker transmissibility tests, we'll talk more about that. Now off to the right, there's all sorts of analyses we do. We have spring mass simple models. We'll talk about some of those today. If we have a multi-degree of freedom system, we can model that as a finite element model. Statistical energy analysis, coupled loads analysis, computational fluid dynamics. Through the course series, we're going to talk about all 5 of those except for CFD. That's out of scope for this course. The bottom right, we have a variety of guidelines and standards and industry and government requirements we have to meet. In the launch vehicle industry, we have SMC-S-016. That's a aerospace corporation wrote that document. There's also MIL Standard 810H. We have to take into account uncertainty margins, P9550, and we'll be talking about those sorts of references and concerns later on. At the bottom, we heavily draw on empirical data, NASA SP8072 for liftoff acoustics, the Wilby method for transonic and max Q, the Martin Marietta document for pyrotechnic shock source levels and propagations, the Steinberg references, as well as a couple dozen others, but those are the main ones to get started. Then off to the left, we've got in-house flight accelerometer data and our tribal knowledge. So anytime a launch vehicle flies or we do any kind of ground test, we collect that data and store it and try and use it to help ourselves for as new vehicles come along as well. So this is sort of the main set of inputs to the MPEs. There could be others as well. So we need to come up with these maximum predicted environments, and then we derive test levels, vibration test levels, and shock test levels from the MPEs. So here we've got a electromagnetic shaker. So you see this cylindrical structure here. Now normally that would be upright. It's a uniaxial vibration machine. But in this case, it's been rotated 90 degrees. It's been attached to the slip table through bolts. And this is so that the shaker system can apply a lateral base excitation to this component. Now this component happens to be an inertial navigation system, and this is courtesy of the ESA, that's the European Space Agency. So the avionics components must be subjected to vibration testing, and we'll talk about shock as well later on. And we want to make sure these components can function properly before, during, and after vibration. So they should be powered and monitored. If it's an electronic component, it should be powered and monitored during the vibration test. If it's just some strictly structural component, then we don't need to power and monitor it, obviously. So we have a couple different types of vibration tests, and these are derived from the MPE, the maximum predicted environment. And the first we're going to call an ATP, or acceptance test. And ATP stands for acceptance test plan or acceptance test procedure. So we're going to do this for 100% of flight avionics components. And if we want to know, well, what constitutes an avionics component, and what about moving mechanical assemblies and pressure vessels and battery boxes and so on, we can go to SMC-S-016, and that spells out what components need to be subjected to acceptance testing. And this will be for 100% of flight units per SMC-S-016. Now, acceptance testing really has two purposes. We want to verify that the parts and workmanship are good to go, and that can be concerns about solder joints, fasteners that might back out if they're not torqued down properly or don't have the proper locking hardware. So we want to make sure that the parts are good and the workmanship, materials, and so on are good to go. But we also want that acceptance test to cover the MPE, which we talked about in the previous slide. So it's a two-in-one purpose, dual-purpose test. Now it kind of sets up a bit of a dilemma, but here's our dilemma that we have. So we can go ahead and test the component, and usually we test these separately in each of three orthogonal axes. And we can acceptance test the component, and let's say it passes. Well, that's great. So the next time the component encounters vibration will be on the launch vehicle. Well, it could be some shipping and handling vibration along the way, but let's just say the next time it encounters vibration will be on the launch vehicle. So how do we know that it's going to still be good to go for the launch vehicle vibration? Because maybe the launch vehicle vibration will be the proverbial straw that breaks the camel's back. And the answer is we can never be 100% sure. But we have a reasonable solution that industry has worked out and that all the major aerospace players follow, and it's SMC-S-016. and that is the qualification or QTP test. So a QTP, what we're going to do, let's just take that inertial navigation system. We're going to take the same part number, but a different serial number. And this different serial number unit, the QTP unit, will never be flown on a launch vehicle, but it's still going to be subjected to shock and vibration tests. But the qualification, the QTP levels, will be higher than the ATP levels, maybe by a margin of 6 dB. That's pretty common. And also the QTP test duration will be longer than the ATP duration. Now we say that that is to verify the design of the component and to demonstrate that the acceptance tested flight unit will have remaining life after it successfully completes its acceptance test. Well, we're also going to include enough amplitude margin and duration so that, well, let's take a look at a scenario. Let's say that during an acceptance test, a bolt backs out or a solder joint breaks. Are we going to scrap that avionics component just due to one solder joint failure? And the answer is no. Some of these components can be, well, maybe $100,000. So we're going to allow for repair and rework. So if a component has to undergo repair or rework, we have guidelines for how much it needs to go and recycle through its acceptance testing. So the QTP level margin duration need to be long enough so that that acceptance test unit can have a potential couple, 2 or 3 cycles of recycling through due to repair and rework, and with some margin to spare for the actual flight vibration. So more about that in SMC-S-016. Now here is just sort of a schematic about what a shaker test is, and we're going to talk mostly about random vibration and power spectral density tests right now, but later on we're going to be also talking about sign dwell and sign sweep. And if the shock level is fairly reasonably low, we can actually do shock testing on a shaker. Not very often, but sometimes. And if the shaker method can be used for shock testing, that's the way to go because that's the most repeatable of our shock test methods. So on the left, you see a control computer. So the operator sits down and the operator types in different parameters, and those parameters include what type of test is it? PSD test, shock response spectrum test, sign sweep, sign dwell, whatever. We have hybrid environments like sign on random. We'll cover those much later. The duration needs to be entered in, the test duration. There's an accelerometer sensitivity factor that needs to be entered in, as well as a whole series of other parameters. So the shaker control computer has to synthesize or generate a time history voltage drive waveform that will be output from the control computer and input to this power amplifier. From there, the signal is applied to the shaker table. This is a voltage time history signal. Now the shaker table is similar to a loudspeaker. It's got a field coil and an armature, and it's going to be a uniaxial shaker vibrating up and down. There's a test fixture mounted atop the shaker, and then the test item, which could be an avionics component, is mounted on top of that fixture. Now, if this component needs to be tested in each of 3 axes, then it can be rotated around and placed on different faces, like the side faces of that fixture to get the other axes. Or if it's a larger component, we may need to do a slip table test like shown in the previous slide. Now, this accelerometer is very important. It forms a feedback loop. And feedback occurs in several contexts throughout this course series. This is the first context of a feedback loop. So in order to have a controlled test, the accelerometer returns that feedback signal to the control computer. It's a voltage time history, but the computer can apply the accelerometer scale factor to determine the G's per time, and then do whatever Fourier transforms or other calculations are needed to get a PSD in the case of random vibration. Now the control computer will then adjust the output signal in order to better meet what the specification is. So the specification is going to be the base input. So where the test item meets the fixture, there's a base input. Now this diagram is actually oversimplified because in reality there would be at least 2 control accelerometers. I'm only showing one for brevity. And even for a well-behaved small item on a cube fixture, it's a good idea to have 2 control accelerometers. For control stability, there could be some fixture shaker resonances going on, or shaker rocking, or otherwise some spatial variation across the top of that fixture. So we need at least 2 control accelerometers. If we've got a larger test article, or maybe we've got a slip table set up, we can have 6 or 7 or 8 control accelerometers. Now we may have an additional accelerometer, let's call it a reference accelerometer, that might be mounted on top of the test article itself. And that is a method by which we can get what's called a transmissibility measurement and determine what the component's natural frequency and damping values are. So it's quite common to have a reference accelerometer that's not used for control, it's just used to get responses as well. Now shock testing, there's various ways of doing this. This is a common way nowadays. And if you look, let's start over to the right. You can see there's some small component. I'm not even quite sure what this is, but this is a NASA JPL, Jet Propulsion Laboratory, set of photographs there. So the small component is mounted on a fixture, a cube fixture on one face of it. And you can see there's a couple of accelerometers there in the various axes. And the test conductor gets to control or gets to decide the setup parameters. Now the setup parameters are going to be, you see there's this beam here, and probably off to the left or right or someplace elsewhere in this room, there is a big array or stack of beams of varying thicknesses, and some would be steel and some would be aluminum. So the test conductor picks which beam, and then he or she would then do some other adjustments. You see these blocks here have these tall bolts, and these tall bolts go into slotted holes. So these blocks can be moved to the left or to the right to control the length of the beam in terms of the inside faces of those blocks there. So that's another parameter the test conductor can control, or for the setup, that is. Now on the underside, there's a cylindrical device, and that's actually an air gun, sometimes called a cannon. It's charged up with air pressure, and then the pressure is suddenly released, and it's going to drive a projectile to the underside of that beam. And that projectile, again, the test conductor can decide what type and size and mass of projectile to use, as well as what should be the initial pressure, in terms of potential energy of that air gun. So what the test conductor would do is, prior to the test, is the actual component would not be mounted on the cube, rather maybe a mass simulator would be mounted. And then the test conductor is going to do some trial and error experimentation, determining what set of parameters are needed to get the required level for the specification. So this is a common way. There's actually a commercial version of this that's out there. And then there are yet other ways of doing mechanical shock testing. We'll cover those later on. I've got a note here that shock testing of this sort is normally done only as qualification. We don't want to do an acceptance shock test on flight components because of the potential for inducing damage, and we just don't want to go there. Okay, so I mentioned power and monitoring the components, at least electronic ones, during vibration tests as well as shock. And we're going to talk about failures that can happen, but before we talk about failures, we're going to talk about malfunctions. What is a malfunction? Malfunction is where something goes off nominal, but nothing actually breaks. So let's think about electromagnetic relays. We can, switches, and we can even make an analogy to hydraulic or pneumatic valves. So again, these components for the launch vehicles must withstand liftoff and ascent vibration, as well as pyrotechnic stage separation and fairing separation type shocks. In some cases, there's reentry vibration. In the case of reusable launch vehicles, there's the descent and landing environments as well. So let's take a relay that is normally closed. So under shock or vibration, the contacts may open up, and that's called chatter. If the shock and vibration inducing that. Well, is it okay if a normally closed relay all of a sudden is open for a millisecond or so? Well, maybe, maybe not. Again, this is not a heart failure because nothing breaks, but it could adversely affect the performance or cause some other type of failure. There's even something called change of state, where a normally closed relay or switch goes to open or vice versa. And valves, they have their own set of similar issues. A valve that's supposed to be closed may cause a leak of a fluid or gas under shock or vibration. Well, how much, if any, leakage is acceptable? Well, that's something that needs to be thought about, and there's some concern there that we have. So nothing actually breaks, but these components are not operating as designed due to the chatter or the leakage type effects. So we have to be on the lookout for that. Well, then there's the set of hard failures. So this set of images here are solder joint failures. Solder joints and lead wires can be fragile. Fatigue failure in particular is a concern, and that can happen due to thermal cycling, vibration shock, or some combination of environments. Now, the set of image, I just pulled off various web pages. I probably should have documented the references, but so I can't say for sure whether these are thermal cycle or vibration failures or combination, but nevertheless, these are representative of what can happen in a vibration test environment, and I've seen these type of failures occur. The solder joints, during the solder processing, there may be some voids or foreign objects, debris, or inclusions, or something that then becomes a stress concentration factor, and that can be a likely location for a crack to initiate and then propagate. And then when the solder joint fails, then that creates an open circuit, which, that's a hard failure. Now we're going to continue on with that, and in some cases it's not just a single solder joint failing, or it could be the whole piece part detaches from the circuit board. I've actually seen this. This is what can happen particularly in shock testing. So think about that pyrotechnic simulation using mechanical impact method like we saw in a previous slide. So we're going to talk about staking. Now staking is where a component is glued down via adhesive like an epoxy, RTV, silicone. There's a number of commercial staking compounds out there. And the rule of thumb is that staking is needed for parts weighing more than 5 grams. And the European Space Agency kindly provided this image to us. And they have some mention there about high shock loads above 2,000 SRSGs and circuit boards deflecting and high relative deflections inducing stress in the solder joints and lead wires there. We'll be talking more about that as we go along in the course series. Now here's another type of piece part. It's some kind of inductor coil. Maybe it's what's called an RF choke. And someone had the idea that lacing cord could be used, that nylon lacing cord, to protect the component under a shock environment. Well, even so, you see that kind of turquoise or aquamarine arrow there pointing to a fracture that occurred. So this lacing cord was not sufficient for the shock environment. So the takeaway was that this piece part should have had staking, which it did not. Now, some of you are thinking, well, I don't do, referring to yourselves, don't do any microelectronics. That may be true. Many of you may not. But there's other types of vibration failures that can happen if all you're dealing with are beams, plates, shells, mechanical machine parts, or so on. So at the top left, you see a mountain bike, and it has a welded joint. Well, welds, kind of like solder joints, can have voids or inclusions or foreign objects and debris or so on during the welding process. And again, stress concentration factors and cracks can form. And There's other problems that can happen with welding if you've got different types of materials as they cool down, due to differential coefficients of thermal expansion. Warping can happen, and there's all sorts of things that can go wrong during the welding process, and so these cracks can start to form. And as the rider is going over rough terrain and maybe getting airborne or so on, that puts a lot of stress on those joints, and that can cause a fatigue failure. Now at the bottom we've got a turbine disc there, and it seems like about every other year there's a news story about some aircraft that lost a turbine disc due to fatigue, or a turbo fan blade, for example, or a vane, or some sort of failure happened due to fatigue. And these discs, how many rotations do these turbine discs undergo during their lifetime? I don't know, 100 million. I don't know. It's some vast number. In the top there, you see a spring with a fatigue failure, and you kind of look at that little pattern of ridges. And we're going to talk later about those pattern of ridges, that surface roughness. Well, what became the surface. That can tell us the story of what type of loading and what type of fatigue failure occurred. We'll talk more about that later on. At the bottom, we've got a landing gear. So think about a commercial aircraft undergoing tens of thousands of landings. And there's something called a hard landing, for example. And it depends on the runway surface. It depends on if there's wind shears, wind gusts, the state of the tires, the air pressure, the pilot's skills, obviously. The pilot, there's a certain descent or sink rate that comes into play. That the pilot has to do a slight pitch up or flare of the nose prior to landing so that the back wheels touch down first, and then the nose gear following that. And all those factors will determine the G level. Now, the G level in landing is monitored on all these commercial flights that you've taken. And if the G level is high enough, that will trigger inspection and maintenance. So think about all the different landing shocks, especially the hard landings that the aircraft landing gear has to endure. And that can, in some cases, cause fatigue cracks and failures. Off to the right, we see two golf club heads there and fatigue cracks that happened. And as I think about that, I see all those indentations and so on. And I suppose those are desirable to help the trajectory of the ball along its ways to get the optimum drive. But those little grooves and indentations then become stress concentration factors, and where cracks can initiate and propagate. So I don't know if those golf club heads are covered by warranty or not, but that's something that can happen. Flex hoses, so if you're working in the launch vehicle industry and you've got liquid engines, then you're going to have flex hoses that can carry high temperature, high pressure fluids or gases, and the hose may spring a leak, as shown in the top left there, under cyclical loading and fatigue. So on the top right, you see a circumferential crack that happened, and the bottom left, it's mostly a longitudinal crack that happened. So these flex hoses have to be analyzed and tested and designed to withstand cyclical loading, especially if it's an engine on a vehicle that where the engine is going to be reused over a course of a dozen or 2 dozen flights. So a recommended textbook for this course series is Steinberg. It's an excellent book. Some of what we do in this class is taken from Steinberg or otherwise inspired by Steinberg. And this is vibration analysis for electronic equipment. And if all you do are beams, plates, and shells, this is still an excellent reference to have. It goes very light on theory and partial differential equations, and it has quite a few hand calculations. It is an excellent book. I highly recommend it. Now I've got a Slinky demonstration here where we're going to talk about natural frequencies and kinetic and potential energy and a few other things. So let's go ahead and listen and watch this video here. Let me get started. Slinky, and I'm holding it upside down, and I'm going to give the Slinky an initial displacement. Now, after I release it, the stiffness property from Hooke's law will try and pull the slinky back to its equilibrium or rest position. But the slinky is going to overshoot the rest position mark due to its mass or inertia. So there's going to be an interplay of kinetic energy from the mass, and there's going to be an interplay with the stiffness and potential energy, and that's going to occur at the natural frequency of the slinky. So here I am, I'm releasing the slinky, and it's going through a couple of cycles of oscillation, each time overshooting the rest position. Now eventually it does return to the rest position after a number of cycles oscillating at its natural frequency. And the reason it returns to its rest position is due to damping, which is an energy dissipation mechanism. So there's different frictional effects happening within the coil that cause damping. There may be some air resistance damping and some boundary damping in my hand. Now here's the interesting thing with the slinky. So let's see what we can do with the slinky. Let me give it initial displacement again. And this time the slinky is not returning to its rest position. And the reason is I'm exciting this at its natural frequency, which is called resonance. So there's a very subtle motion going on with my hand, which you can probably just barely see. But I'm moving my hand at the natural frequency of the slinky, causing it to go into resonance. And there's a dynamic amplification factor occurring, so that if the motion of my hand is maybe 1 unit, it could be 10 or more units of response at the base of the slinky. Now, even though my hand's at the top of the slinky, we would call this base excitation or support motion, or it could be called seismic excitation. So this could represent, for example, an earthquake exciting a building, although in the case of an earthquake, the motion would be more random rather than sustained sinusoidal oscillations. So there's several concerns about this. One is if a structure is excited at its natural frequency, it could be a failure due to fatigue or yielding or ultimate stress limit or buckling maybe. And then the other one we have to be concerned about in some cases, particularly for low frequency oscillation, is loss of sway space. Okay, so hope you enjoyed that video. Let's move on. So the basic model in all of vibration analysis is the spring mass system. At the top left, you see the mass M, and Hooke's law gives the spring stiffness K. We've got C is the viscous damping coefficient, X is the absolute displacement of the mass. We've got a free body diagram off to the right there. And the natural frequency of this system then, omega sub n, will be the square root of the stiffness K over mass M. And this is angular natural frequency, so typically radians per second. So the fundamental problem in all of vibration is to determine either through analysis or test what the natural frequency will be of the component or system or beam or plate or shell. And you just saw a video where we demonstrated the natural frequency of the slinky. So just sort of review some of the things in the video. This natural frequency is the frequency at which an exchange occurs between the kinetic and potential energies. And resonant occurs when the system is excited at its natural frequency. And resonance may cause fatigue failures or some other type of failure mode. Now, obviously there's other failure types that can happen. We can have non-resonant failures, but in the world of vibroacoustics, we're primarily concerned about what happens at resonance, because that is the most likely condition for fatigue or other type of failure. So the fundamental problem in all of vibration, vibroacoustics, is to determine the natural frequency. by test or analysis, or preferably both. Now the damping, there is no Newton's law for damping. There's no free body diagram to help us predict what damping is. Damping can only be measured. But if you have some new component that's you have not even built a prototype yet, we can draw upon reference databases for damping, or sometimes we just have to assume a lower and upper bounds for damping as we go along. So we're going to take a look at this calculation, which, as simple as it may seem, gets a little tricky when we're in the English system. So here we have a spring mass system, and it's going to be 5 pounds mass. Now, I'm going to be very careful about mass. I'm never just going to say pounds. So this is LBM, or pounds mass, and then the spring stiffness is 20,000 pounds force, or LBF per inch. Now an LBM is not the same as an LBF. Those are two different parameters. So in order to get the natural frequency, we're actually going to have to be very particular about units, and we're going to have to do this very awkward conversion you see in the denominator there to get all the units to work out like they should. And when we do this, for this problem, we get 1243 radians per second. Now, if you're using the metric system, this calculation is much simpler. But here we are with the English system, so we have to apply this unit correction or conversion factor there. Now, in the world of vibroacoustics, we seldom deal with radians per second. Instead, we like to get the natural frequency in hertz, which means we divide by 2 pi, and that comes out to be approximately 200 hertz. And these numbers were chosen deliberately because, for say, example, a circuit board, it's typical that some circuit boards would have their natural frequencies around 200 hertz. So maybe there's a 5-pound avionics box, and somehow or another we're modeling the stiffness as 20,000 pounds force per inch, and there's a circuit board inside, and the system together is vibrating at 200 hertz. Now I've got a MATLAB GUI package that goes along with this course, so let's see what we can do with our GUI package. So we go to open up the GUI package called vibration data _ app, and we go to the structural dynamics tab, and then we can, single degree of freedom, natural frequency in response to initial conditions. So if you need to, if you're doing this, following along, you can stop this presentation any time to get caught up, or pause it, that is. And then we go to this natural frequency. There's our spring mass system. So even if we have a complex structure that as a first approximation, we like to model it as a single degree of freedom system. So this by far is the most common model in all of vibroacoustics. So we're going to calculate the natural frequency. We've got our 5 LBM and 20,000 LBF per inch. Now this program is very useful because it takes care of all that bookkeeping, all the unit conversion, and so on. And the natural frequency, and we like to do rounding in vibroacoustics. We're going to round that and say that that's a 200 hertz natural frequency. So you're welcome to use this utility as you see fit. So just sort of a review here, the natural frequency is the frequency at which a mass will vibrate if given an initial displacement and then released so that it vibrates freely. And this is also called simple harmonic motion, particularly if there's no damping present. An object has both mass and stiffness, and the spring stiffness will try and snap the object back to its rest position if it's given an initial displacement. Just like that slinky, except as we saw, there's an inertial effect, or mass, which causes the object to overshoot its rest position, and it goes back and forth a number of cycles. And that back and forth motion is occurring at the natural frequency. And again, there's that exchange of potential and kinetic energy at that natural frequency. And we're going to take a look at a tuning fork here. So these two forks here are called tines. And for the fundamental mode of the tuning fork, the two tines are going to move 180 degrees out of phase. So they're either going to move towards each other and then return back to neutral and then move away from each other. So it's an in-plane bending vibration. And you really can't tell, but the stem is also participating in that fundamental mode as well. Now I've got a time history from a tuning fork. I did a little science project, and I was actually able to drive the tuning fork into its fundamental mode, and I used magnetostriction. And we'll talk more about magnetostriction later on, but that's the method I used. Basically, I took a electromagnetic coil and draped it over one of the tines of the tuning fork and applied a steady state sinusoidal voltage signal, but more about that later on. And here we've got the unscaled sound pressure along the y-axis, and we've got the time in seconds along the x. This is experimental data, and it's not pure sine, but for experimental data, that's about as close as you're going to get to a pure sine function. So for this well-behaved single frequency, or very nearly a single frequency, we can just count the number of peaks over a time duration and estimate the natural frequency, which comes out to be 440 hertz. On a musical scale, that is an A note. Now, counting the peaks divided by time, again, works for a well-behaved case. Later on, we're going to talk about what's called the positive slope zero crossing rate, which is a little bit more rigorous way to go about doing that estimation. But what I've shown there works well enough. We can actually do this exercise in MATLAB. So again, I've got the GUI package, I've got the import data tab selected, and then acoustic time history, and then tuning fork, and read in the data. And we can read in that data to MATLAB. It's a library function. See, library tab is also selected there. And we can call that in. That's the same sound pressure time history, uncalibrated, as we saw on the slide. So we've got a couple different ways of estimating the frequency. We've already done the count the peaks and divide by time. We can do Fourier transform, except we're not going to do Fourier transform today. That is going to come in a later unit. Well, another method we can use is we can take a textbook sine function and use what I call a hybrid least square curve fit approach. And if we can calibrate that textbook sine function to match the data reasonably well, that's an indirect method to determine the frequency. So we are going to go to signal analysis. Okay, got to fix that a little bit, but time history, pressure, sine and damp sine curve fit, and analyze signal. It's back on the MATLAB GUI package. Come to this function screen here. So this script performs either a sine or damp sine curve fit on a time history. The input array must have two columns, time in seconds and amplitude. Now, I've got this software configured, so it's going to go out to the workspace and see what is available, what two-column time history is available. And we see that that tuning underscore fork that we just read in on the previous slide is available. Now, if you're using this package and you're doing a bunch of imports and doing a bunch of work, sometimes you have to click on Update List to see, the time history that you're looking for there. Let's see, tuning fork, we'll call that the plot title, unscaled sound pressure. We're going to plot the time history. Now, as we do this curve fitting, we don't have to do the whole signal. In fact, usually we're just going to do a small segment. Well, in this case, the data is so well behaved, we're going to take the whole 0 to 0.5 seconds. We know that the frequency is approximately 440 hertz, but we'll open up the max frequency to 1,000. It's just kind of good to be extra conservative. Downsample per max frequency, yes. We've got some options. We can pick sine or damp sine, and we're going to pick just sine. And we could have multiple sines, but in this case, we just have a single sine we're looking for. Then we calculate, and we get those results off to the right. We're not so much interested in the amplitude, since it's unscaled sound pressure anyways, and the phase angle we're just not interested in. But that frequency, we are, 442.3 hertz. Now, nominally, that's an A note. That's what it said on the package. And an A note is 440 hertz. Well, of course, there's some material imperfection. There's manufacturing tolerances. And it's experimentally, it comes out to 442.3 hertz. Well, that's close enough. Close enough. Now, as we see this number, we're still not sure that's the right number. So we have to look at something else. and that's the graphical representation. So on the next slide, we see we've got unscaled sound pressure, Y, time in seconds, X. The blue curve is our measured data, that's input. And the red curve is a synthesized, it's a hybrid least square type curve fit. It's got some trial and error and a few convergence thing built in. But basically, the red curve is our textbook function. Now, as we just do what I call the eyeball check, we say, well, that's just about as good as you could expect to get. Now, another thing you might notice, we actually were doing the curve fit from 0 to 0.5 seconds, but I'm only plotting from 0 to 0.2 seconds just so we can take a closer look at what's going on. But that passes our eyeball test with flying colors. So I would say then that 442.3 hertz, that is a good number that we have a high amount of confidence in. So I hope you enjoyed this unit. There's going to be a part 2, but that is all for now.